Look at your hand. Hold it up to the light. Turn it over. See the lines, the texture of the skin, the faint blue pathways of the veins beneath. It feels solid, does it not? It feels real. It feels like an object, a thing in the world, separate from the air around it, separate from the light that touches it. This feeling, this certainty of touch and form, is the most profound and comforting story you have ever been told. It is also a lie. Not a malicious lie, but a necessary one. A convenient fiction spun by your senses so that you can navigate the world without going mad. Because beneath the surface of that hand, beneath the skin, beneath the cells, beneath the molecules, there is a ghost. There are ghosts, trillions upon trillions of them. They are not the ghosts of spirit or folklore. They are the ghosts of existence itself. They are the fundamental constituents of your being, and they do not obey the rules of the world you think you know. They are a whisper, a probability, a mathematical specter haunting the house of reality. This is the quantum world. It is not a place somewhere far away in the cold of space or the heart of a star. It is here. It is now. It is the very bedrock of the chair you're sitting on, the air you are breathing, the thoughts you are thinking. It is the silent, invisible engine that builds the illusion of solidity you call your hand. And to understand it, even a little, is to have the world you know dissolve like salt in water, leaving behind a shimmering, unsettling, and beautiful mystery. We're going on a journey into that mystery, not with equations, not with chalkboards, but with questions, with a willingness to let go of what feels certain. Are you ready to meet the ghosts that build your world? The great lie is solidity. You press your hand against the table. It stops. Two solid objects meeting. This is the first lesson of childhood, the first rule of the physical world. Things are solid. They have boundaries. They occupy a single, defined space. But what is actually happening in that moment of contact? What is this thing you call a table? What is this thing you call your hand? Let's dissolve the illusion layer by layer. First, we see the surface. Wood grain, polished and smooth. Skin, patterned with unique whorls and lines. But zoom in. Magnify the view, past what the eye can see, past what a simple microscope can reveal. The surfaces are no longer smooth. They are mountain ranges of imperfections, valleys and peaks of cellular structures, of wood fibers. What felt like a perfect plane of contact is revealed to be two jagged coastlines, barely touching at their most extreme points. But this is still the world of things. Let's go deeper, into the cells of your skin, into the complex architecture of proteins and lipids. We push past them, down into the molecules themselves. Long chains of carbon, hydrogen, oxygen. Complex, beautiful structures, vibrating with thermal energy. And now, we take the final plunge. We go to the heart of the matter. We find an atom, a single carbon atom, perhaps in a protein molecule in a skin cell in your finger. What do we find? We find nothing. Almost entirely, wonderfully, terrifyingly nothing. There at the center is a nucleus, a tiny, impossibly dense collection of protons and neutrons. If this atom were the size of a grand cathedral, the nucleus would be no bigger than a grain of sand floating in the very center. And the rest? The vast, cavernous space of the cathedral? It is the domain of the electrons. But the electrons are not little planets orbiting a central sun, as we were once taught. That, too, is a comfortable story, another convenient fiction. The electron is not a thing. It is not a tiny ball of anything. It is a cloud, a haze of probability, a region of space where the electron might be. It is nowhere in particular and everywhere at once within its designated shell. It is a smear of potential, a mathematical description of a ghost. So when your hand, made of these atomic cathedrals of empty space, presses against the table, also made of these cathedrals, what is touching what? Nothing touches. Absolutely nothing. The feeling of solidity, that bedrock certainty of your physical experience, is an illusion created by force. The probability cloud of the electrons in your hand gets close to the probability cloud of the electrons in the table. And these clouds, both being negatively charged, repel one another with ferocious power. You are not touching the table. You're feeling the electromagnetic force pushing back. You are floating in infinitesimal distance above the surface, suspended by a field of invisible energy. Your entire world of solid objects is a mirage. It is a universe of ghosts held in place by invisible threads of force. You are not a solid object. You are a collection of impossibilities, a swarm of probabilities, a complex pattern of energy and information that has learned to call itself I. And this realization, this deconstruction of the simplest, most obvious fact of your life, is the doorway. It is the first step into the strange and profound world that lurks just beneath the veil of your senses. How we come to know this? How did humanity stumble upon a truth so contrary to every intuition we possess? It was not a willing discovery. Reality had to be dragged, kicking and screaming, out of the comfortable world of classical certainties. The journey begins at the turn of the 20th century. Physics felt complete, a magnificent clockwork universe designed by Newton, polished by Maxwell. The laws of motion, of gravity, of electromagnetism, they seemed to explain everything. The cosmos was a grand, deterministic machine. If you knew the position and momentum of every particle, you could, in principle, predict the entire future of the universe. It was a beautiful, tidy, and utterly wrong idea. There were just a few small cracks in this perfect edifice, a few nagging problems that refused to be solved. One was a puzzle called the black body radiation problem. Imagine a perfect oven. As you heat it, it glows. First red, then orange, then yellow, then white hot. Classical physics tried to predict the spectrum of light, the colors, that this ideal oven should emit at a given temperature. And it failed, spectacularly. The existing equations predicted that as you looked at higher and higher frequencies of light, into the ultraviolet and beyond, the oven should be emitting an infinite amount of energy. This was absurd. It was called the ultraviolet catastrophe. It was a signal that the beautiful clockwork machine was fundamentally broken. Into this crisis stepped a man named Max Planck. He was a conservative physicist, a man who deeply respected the classical tradition. He had no desire to be a revolutionary. He just wanted to solve the puzzle. In the year 1900, after years of struggle, he found a solution. It was a mathematical trick, a fudge factor he hoped would later be explained away. He proposed that energy was not emitted smoothly, like a continuous flow of water from a tap. Instead, he suggested, it could only be emitted in discrete little packets, in chunks. He called these packets quanta. It was as if you could not pour water, but could only have it in the form of individual ice cubes. His equation worked. It perfectly described the glow of the oven, but the cost was immense. It introduced a graininess, a lumpiness, into the smooth fabric of energy itself. Planck himself was deeply troubled by his own discovery. He called it an act of desperation. He had solved the problem, but he had shattered the foundation of physics to do it. He had opened a door, and he was afraid of what lay on the other side. Then came the visionary, the man who was not afraid to walk through that door, Albert Einstein. In 1905, his miracle year, Einstein took Planck's desperate idea and declared it was not a mathematical trick. It was real. He used it to explain another nagging puzzle, the photoelectric effect, where light shining on metal can knock electrons loose. Einstein proposed that light itself was made of these quanta, that a beam of light was not a continuous wave, but a stream of tiny particles, of light bullets. These particles would later be named photons. And here, the first great paradox of the quantum world was born. For a century, experiments had proven beyond any doubt that light behaves as a wave. It diffracts, it interferes, it spreads out like ripples on a pond. Now, Einstein was saying it was a particle. How could it be both? How could a thing be a continuous, spreading wave and a discrete, localized particle at the same time? It defied all logic. It was like saying something was both a mist and a stone. This was the core problem. the impossible duality that would haunt physics for decades. Nature, at its most fundamental level, refused to be one thing or the other. It insisted on being both. The third great pioneer of this new world was Niels Bohr, a Danish physicist who was part poet, part philosopher. If Planck opened the door and Einstein walked through it, Bohr was the one who tried to draw a map of the strange new land. Bohr applied the quantum idea to the atom itself. He created a model of the atom where electrons could only exist in specific energy levels, specific orbits, like steps on a ladder. They could not exist in between the steps. To move from one level to another, an electron had to absorb or emit a single quantum of light, a photon. And in a truly bizarre leap, he declared that an electron jumps from one orbit to another without traveling through the space in between. It simply ceases to exist in one place and simultaneously begins to exist in another. Think about that. An object vanishing from here and instantly reappearing over there without a journey. It was magic. It was madness. But it explained the spectral lines of hydrogen perfectly. These men, these reluctant revolutionaries and bold visionaries, had uncovered the first rules of a world that did not want to be understood in human terms. They had found a place where particles are waves, where energy comes in lumps, and where movement can happen without travel. They had followed the cracks in the old reality and found a universe far stranger, far more mysterious than they had ever imagined. The tidy, predictable clockwork was gone forever. In its place was a world of ghosts, of probabilities, and of paradoxes that still challenge the very meaning of the word real. So what are the inhabitants of this ghostly realm? What are the fundamental pieces from which you and the entire cosmos are assembled? Science has given them names, a taxonomy of the strange. But do not let the names fool you into thinking they are simple things. They are not tiny marbles. They are labels for specific kinds of mathematical behavior, specific flavors of existence. First, there are the quarks. You have never met a quark on its own. You never will. It is a fundamental rule of this universe that a quark cannot exist in isolation. They are the ultimate social particles, found only in groups of 2 or 3, bound together by the most powerful force in nature. The protons and neutrons in the nucleus of every atom in your body are each made of 3 quarks. There are 6 types of them, 6 flavors, a whimsical name for a profound distinction. Up and down, the most common, which build all the stable matter around us. Then there are their more exotic, heavier cousins, charm and strange, top and bottom. These particles lived in abundance in the fiery chaos of the Big Bang, but now exist on Earth only for fleeting moments, created in the heart of particle accelerators before decaying back into their more stable relatives. But the strangeness does not end with flavor. Quarks also possess a property called color. This has nothing to do with visual color. It is another poetic label, another metaphor for a charge they carry. The colors are red, green, and blue. And the rule is this: any group of quarks bound together must be color neutral, just as mixing red, green, and blue light gives you white light. A combination of a red, a green, and a blue quark creates a stable, colorless particle like a proton. Think of the utter weirdness of this. The building blocks of your reality have a property that behaves like color, and they are forbidden from ever being seen alone, forced by the laws of physics to huddle together in groups that cancel out their own defining characteristic. They are prisoners of their own nature. Then there are the leptons. The most famous of these is the electron, the ghostly cloud that defines the size and chemical properties of atoms. Like quarks, leptons come in generations. There is the electron and its heavier, unstable siblings, the muon and the tau. And for each of these, there is a ghost, the neutrino. Neutrinos are almost nothing at all. They have a tiny, tiny mass, but so small it was long thought to be zero. They have no electric charge. They barely interact with anything. Right now, trillions of neutrinos, born in the heart of the sun and in distant cosmic cataclysms, are streaming through your body, through the chair, through the entire planet, as if it were empty space. Almost none of them will ever notice you are here. They are the ultimate messengers from the cosmos, carrying information from the hearts of stars and the beginning of time, and they pass through us completely unheeded. They're the closest thing to a true ghost that physics has ever found. These particles, the quarks and the leptons, are the family of matter. They are the stuff. But what holds the stuff together? What governs their interactions? For that, we need another family of particles, the force carriers, the bosons. Imagine the universe as a grand stage. The quarks and leptons are the actors. The bosons are the messages they pass between each other, telling them how to move, how to behave. Every force is an exchange of a particle. The electromagnetic force, the one that prevents your hand from passing through the table, is carried by the photon. The particle of light. Atoms exchange photons to repel or attract each other, forming the bonds that create molecules, that create you. It is the great architect of chemistry and biology. The strong nuclear force, the one that binds quarks together inside protons and neutrons, is carried by a particle called the gluon. It is aptly named. This force is so stupendously powerful that it actually gets stronger the farther apart you try to pull two quarks. It is like an unbreakable cosmic rubber band. This is why quarks can never be found alone. The energy required to pull them apart is so immense that it creates new quarks from the vacuum, which immediately bind together. The force itself creates matter from nothing to maintain its own rules. The weak nuclear force is the agent of change and decay. It is carried by the W and Z bosons. It is the force that allows a neutron to turn into a proton, a process that is essential for the sun to shine. It is weaker than the other forces and acts over incredibly short distances, but without it, the universe would be a static, boring place. It is the force of transformation. And finally, there is gravity, the grand sculptor of the cosmos. In the quantum world, we believe it too must have a force-carrying particle, the hypothetical graviton. But gravity is so incredibly weak compared to the other forces at the scale of particles that we have not yet been able to detect its quantum nature. It remains the great outlier, the one force that has stubbornly refused to be fully united with the quantum picture. So this is the zoo, a handful of quarks, a handful of leptons, a handful of force carriers, and a set of bizarre, counterintuitive rules. This is the standard model of particle physics. It is one of the most successful scientific theories ever devised, tested to incredible precision. And yet, look at what it describes. A world built of particles that cannot be alone. Particles are also waves, particles that are barely there at all communicating through the exchange of other particles. How do we even know any of this is real? We cannot see a quark. We cannot isolate a gluon. We cannot hold an electron. We know because we see their shadows. We build cathedrals of science, particle accelerators, miles in circumference, buried deep underground. In these great rings, we use powerful magnetic fields to accelerate particles like protons to nearly the speed of light, giving them energies not seen since the first moments after the Big Bang. And then we smash them into each other. It is a desperate and brutal form of discovery. It is like trying to understand how a fine watch is made by smashing two of them together, studying the pieces that fly out. But in the debris of these cataclysmic collisions, in the shower of new, exotic particles that blossom into existence for a fraction of a second, we see the patterns. Our detectors, vast, complex electronic sensors, do not see the particles themselves. They see the trail a particle leaves behind, the energy it deposits, the way it curves in a magnetic field. We see the fingerprints, the echoes, the ripples in the pond. From these fleeting shadows, we reconstruct the events. We use the laws of conservation of energy and momentum and the rules of the Standard Model to deduce what must have been created in that initial fireball. We find the signatures of the top quark, of the Z boson, of particles so massive and unstable they exist for less than a trillionth of a second. We are detectives at a cosmic crime scene, arriving long after the event, piecing together the story from the faintest of clues. The experimental evidence is not a photograph. It is a deduction, a logical chain of inference supported by mountains of data that all points to this one strange conclusion. The world is built from these ghosts. We know they're not because we see them, but because the universe behaves exactly as it should if they were there. The mathematics, born from the minds of Planck and Einstein and Bohr and so many others, predicts their behavior with astonishing accuracy. We see their influence. We see the world they build. But the particles themselves remain forever veiled, forever one step removed from our direct perception. They are ideas made manifest, equations given a fleeting, shadowy form. They're the truth behind the illusion, but a truth we can only ever glimpse indirectly, like watching the shadows of puppets dancing on a cave wall. And it is in this strange, indirect relationship with reality that the deepest paradoxes begin to emerge. The ones that challenge not just our senses, but our very notions of logic, space, and time. Let us go now to the heart of the weirdness. Let us talk about a single particle, a single electron. Where is it? According to the classical world, the world of your intuition, a particle must be somewhere. It has a position, a definite location in space. But quantum mechanics says no. Until you look for it, until you make a measurement to pinpoint its location, the electron is not in any single place. It exists in a state of pure potential, a condition called superposition. Imagine its wave of probability spreading out. This wave describes all the possible places the electron could be. And the truth is, in a way our language is not equipped to handle, the electron is in all of those places at once. It is a little bit here, a little bit there, a smear of possibilities spread across a region of space. It is not that we do not know where it is. It is that the universe itself has not yet decided where it is. The very concept of a location has not yet been applied to it. This is not a philosophical statement. It is a physical reality, proven by one of the most famous and baffling experiments ever conceived, the double-slit experiment. Imagine a barrier with two thin, parallel slits in it. You fire a stream of particles, say electrons, at this barrier. On the other side is a detector screen that will record where each electron lands. If electrons were simple particles, like tiny bullets, you would expect to see two bright bands on the screen directly behind the two slits. Some bullets go through the left slit, some go through the right. Simple. But that is not what happens. What you see on the screen is an interference pattern, a series of many bright and dark bands, like the pattern you see when two sets of water waves overlap. The bright bands are where the waves add up, and the dark bands are where they cancel each other out. This pattern proves, unequivocally, that the electrons are behaving as waves. But wait, we are firing them one at a time. Each electron is a single particle. So how can a single electron, traveling on its own, create an interference pattern that requires something to go through both slits at the same time to interfere with itself? The unavoidable conclusion is as logical as it is insane. Each individual electron, as a wave of possibility, goes through both slits simultaneously. It interferes with itself. The universe does not force the electron to choose a path. The single particle explores all possible paths at once. Its wave of potential passes through the left slit and the right slit, and the two resulting waves meet on the other side and create the pattern of self-interference, dictating the probable places where the electron might finally appear. It is only when the electron hits the detector screen, when a measurement is made, that this wave of possibility collapses, the superposition is broken. The universe, in that instant, makes a choice, and the electron appears suddenly and irrevocably as a single particle at a single point. But what happens if you try to cheat? What if you place a tiny detector at one of the slits to see which path the electron really takes? The moment you do, the moment you observe which slit the electron goes through, the interference pattern vanishes. The act of looking, the act of measuring, forces the electron to behave like a particle. It picks a slit, And if it picks a slit, it can no longer interfere with itself. The pattern on the screen reverts to the two simple bands you would expect from tiny bullets. This is the measurement problem, the deepest, most unsettling mystery in all of science. The very act of observing reality changes what reality is. The universe seems to know when it is being watched. This has profound implications. It shatters the classical idea of an objective reality that exists independent of us. In a quantum world, the observer is not a passive spectator. The observer is a participant. The questions you ask of the universe determine the answers it is allowed to give. If you ask a particle-like question, which slit did you go through? You get a particle-like answer. If you ask a wave-like question, what is the interference pattern? You get a wave-like answer. You can know the path, or you can know the interference, but you cannot know both at the same time. They are mutually exclusive realities. This was the source of the famous, lifelong debates between Einstein and Bohr. Einstein hated this. He could not accept a reality that was fuzzy, probabilistic, and dependent on observation. He famously declared, "God does not play dice with the universe." He believed there must be some hidden information, some hidden variables that we just could not see yet, which would restore determinism and locality. Bohr's response was, essentially, to tell Einstein to stop telling God what to do. Bohr argued that we must accept what the experiments tell us. The quantum world just is this way. A particle's properties are not defined until they are measured. To highlight the absurdity of this, the physicist Erwin Schrödinger devised his famous thought experiment about the cat. Imagine a cat in a sealed box. Inside the box is a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the atom decays, a purely quantum event governed by probability, the Geiger counter will detect it and trigger the hammer, which will smash the vial and kill the cat. According to the laws of quantum mechanics, until we open the box and observe the system, the atom is in a superposition. It is both decayed and not decayed. But the fate of the cat is linked to the state of the atom. Therefore, until the box is opened, the cat itself must also be in a superposition. The cat is simultaneously alive and dead. It is not that we do not know if it is alive or dead. It is that the cat exists in both contradictory states at once. It is only the act of opening the box, the act of measurement, that collapses the superposition and forces reality to choose a live cat or a dead one. Schrödinger intended this as a ridiculous illustration to show the flaws in this interpretation of quantum mechanics when applied to the macroscopic world. But experiments over the last several decades have confirmed that superposition is real. We have created Schrödinger's cat-like states with large molecules, not just single atoms. The weirdness is not confined to the microscopic. It is a fundamental rule. So where does that leave us? It leaves us in a world that is not a collection of things, but a collection of possibilities. A universe that waits for an act of observation to become definite. It violates our deepest sense of logic, our trust in a stable, objective world that exists whether we look at it or not. And the paradoxes do not stop there. They get even stranger. They challenge the very fabric of space and time. If superposition shatters our idea of a thing being in one place, then entanglement shatters our idea of things being separate at all. Einstein called it spooky action at a distance. It was the quantum phenomenon he found most disturbing, the one he used as his ultimate proof that the theory must be incomplete. And yet, once again, experiments have proven Einstein wrong. The spookiness is real. Imagine you create two particles, say, two electrons, in a single event. You arrange it so they fly off in opposite directions, and so that they have a link property. For example, a property called spin. You can think of spin as a particle's intrinsic angular momentum, and it can be measured as either up or down. Let's say our two particles are created so that their spins must be opposite. If one is spin up, the other must be spin down. This is their entangled state. According to quantum mechanics, until you measure them, neither particle has a definite spin. Each one is in a superposition of both up and down. Now, You let these two particles travel far, far apart. One goes to the other side of your laboratory. The other goes to the moon. You then measure the spin of the electron in your lab. The moment you do, its wave function collapses and it randomly settles into one state. Let's say it becomes spin up. Instantly, faster than the speed of light, the other particle, now on the moon, will immediately become spin down. Instantly. There's no time for a signal to travel from your lab to the moon to tell the second particle what state to be in. The connection is immediate. It violates what Einstein called the principle of locality, the idea that an object can only be influenced by its immediate surroundings. How does the particle on the moon know what you measure in the lab? The answer is as profound as it is unsatisfying. They were never truly separate objects to begin with. Even when separated by vast distances, the two entangled particles remain part of a single, indivisible quantum system. They are described by a single wave function. What happens to one is what happens to the other, because in a way our minds cannot grasp, they're still the same thing. The very idea of separation, of distance, seems to be another illusion, a convenience for our macroscopic world that does not apply at the fundamental level. You cannot use this to send information faster than light. The outcome of your measurement in the lab is random. You cannot force it to be spin up to send a 1 and spin down to send a 0, but the correlation is perfect. An observer on the moon, upon measuring their particle, will always find it has the opposite spin of the one you measured at the exact same moment. It is as if the universe is not a collection of separate points and objects, but a single, interconnected whole. A vast, entangled web where a twitch in one corner can be felt in another, without anything traveling through the space between. This brings us to the deepest philosophical precipice. If the fundamental building blocks of reality are not things but probabilities, if they exist in multiple states at once until observed, if they can be linked in ways that defy space and separation, then what are you? You're made of this stuff. You are not exempt from the rules. Every carbon atom in your body, every water molecule, every quark and electron that constitutes your being is a quantum system. You are a walking, talking collection of trillions upon trillions of probability waves, all collapsing and decohering in an impossibly complex dance. The solidity you feel, it is the statistical outcome of an immense number of quantum interactions. It is the emergent property of a system so vast that the probabilities average out into near certainty. You are solid for the same reason a casino always wins in the long run. The laws of large numbers smooth out the underlying randomness. But the randomness is still there, at the heart of you. Think about what this means for your sense of self. What is a you in a probabilistic universe? Are you just a complex standing wave? A stable pattern in the quantum foam? Are your thoughts, your feelings, your consciousness simply the macroscopic manifestation of this underlying quantum dance? When you make a choice, when you decide to lift your hand, what is actually happening? Is it the deterministic firing of neurons in a classical, clockwork brain? Or is there something more? Is the act of conscious choice itself a form of quantum measurement, collapsing the potential states of your own neural network into a single, definite outcome? This leads us to the most speculative and most tantalizing of ideas: the connection between consciousness and the quantum world. The measurement problem forces us to confront the role of the observer. Something about the act of measurement or observation collapses the wave function. But what qualifies as an observer? Does it have to be a conscious human with a clipboard? Does a Geiger counter count? Does a rock observing a photon by absorbing it count? This is one of the most fiercely debated questions in physics. Some theories propose that any interaction with a large, classical system is enough to cause decoherence, to collapse the superposition and make reality definite. In this view, consciousness has no special role. The universe is constantly measuring itself. But a more radical, more mind-bending idea lingers. It was first proposed by pioneers like John von Neumann and Eugene Wigner. What if consciousness is the one thing that is not just another physical system? What if consciousness is the true observer? What if the universe exists as a shimmering sea of infinite possibilities, a vast superposition of every potential reality, until a conscious mind looks at it, and by looking, forces it to choose one path? In this view, you're not just an observer of the universe. You're a co-creator of it. Your every conscious moment could be an act of collapsing the quantum wave function, turning pure potential into actual, experienced reality. This is not a mainstream scientific theory. It is a philosophical speculation born from the deep weirdness of the physics. There is no proof, but it is an idea that refuses to go away because the measurement problem remains so stubbornly unsolved. It asks the ultimate question: does the universe create consciousness? Or does consciousness, in some way, create the universe we experience? And so, we are forced to redefine our most basic words. What does it mean for something to be real? Is the wave function real, this mathematical object that describes all possibilities? Or is only the collapsed, measured outcome real? Is the electron real when it is a cloud of potential, or only when it appears as a dot on a screen? If the fundamental components of our world do not have definite properties like position or spin until they're measured, can we even call them things anymore? Perhaps reality is not made of things at all. Perhaps it is made of information. This is another modern perspective, that the universe, at its core, is not matter and energy, but bits of information. A quantum bit, or qubit, is the fundamental unit. Unlike a classical bit that is either a 0 or a 1, a qubit can be a 0, a 1, or a superposition of both. Maybe the entire universe is a giant quantum computer processing information, and what we perceive as particles, forces, space, and time are just the output of this cosmic calculation. Reality, then, is not a substance. It is a relationship. It is the interaction between information. The entanglement between two particles is not spooky action. It is just a permanent correlation in their information content. The collapse of the wave function is an update of information, the moment a potential bit becomes a definite one. In this view, you are not a collection of particles. You are a complex, self-sustaining pattern of information. Your consciousness is the process by which that information becomes aware of itself. This doesn't solve the mystery. It just reframes it in a new language. But it is a language that brings us closer to a universe that feels less like a machine and more like a thought. A great, unfolding idea, generating the illusion of a physical world from a substrate of pure information. What then is the universe? A clockwork machine? No, that dream died with Planck. A collection of solid objects? No, that illusion dissolves in the empty space of the atom. A set of tiny particles playing billiards according to fixed rules? No. The double-slit experiment showed us that particles are also waves, and that the rules themselves depend on how you look. So what is it? We are left with metaphors, the language of poetry and philosophy, because the language of common sense has failed us. We began this journey by looking at your hand, at its reassuring solidity. We have dissolved it into atoms, into probability clouds, into force fields. We have seen that its building blocks defy logic, exist in multiple places at once, and remain connected in ways that transcend space. We have seen that the act of looking at it changes what it is. So we return to the central question: what is real? The answer quantum mechanics gives us is not a statement, but an invitation. It tells us that reality is not a static noun. It is an active verb. It is a process. It is a dance. It is a dance between possibility and actuality. A dance between the wave and the particle. A dance between the observer and the observed. The universe is not a finished book that we are simply reading. It is a poem that is being written, and we, the conscious observers, may be holding the pen. The rules of grammar are the laws of physics, strange and beautiful. But the story itself might be one we are helping to create with every glance, with every question we ask. Perhaps the final, unifying metaphor is that of a symphony. Before the conductor raises the baton, the symphony exists only as potential, as ink on a page. It is a superposition of all possible interpretations: fast, slow, loud, soft. The act of observation, the conductor's choice, the musician's performance, collapses that potential into a single, beautiful, fleeting expression of the music. A reality is created in time. But the score, the underlying wave function of possibility, remains. Another performance tomorrow night might be different. Another reality might unfold. The universe is this grand, self-playing symphony. The laws of physics are the score. The particles are the notes, existing as pure potential until they are played. And we, the emergent patterns of consciousness, are both the audience, marveling at the performance, and perhaps, in some way we do not yet understand, the musicians themselves. We are the universe's way of listening to its own music. So look at your hand one more time. Do not see it as a solid, simple thing. See it for what it is: a temporary miracle, a configuration of stardust held together by invisible forces, a trillion ghosts dancing to a quantum rhythm, a complex pattern of information that has woken up and is now contemplating itself. You are a piece of the cosmos that has become aware. You are built from the paradox and the mystery. The strangeness of the quantum world is not out there, in some distant lab. It is in your bones, in your breath, in your every thought. To accept this is to let go of the need for certainty, and to embrace a reality far more magical and interconnected than we ever dared to imagine. It is to find a deep comfort not in knowing all the answers, but in living within the splendor of a beautiful, unanswerable question. You are not separate from the mystery. You are it, a wave of possibility in an ocean of being, collapsing for a moment into the singular, precious experience you call your life.